Hi everyone, I take this opportunity to welcome you to my YouTube channel. IBM is my name, and I welcome you to my channel. It's good that we shall be learning together. Okay, today I'm interested in only grade 11 stroke year 12, as the unit I will be introducing, or the unit I will be going through with you, or the unit I will be going through today is called deformation of solids. Before deformation of solids, we must have studied a unit called force, density, and pressure. And when you looked at force, you must have mentioned some of the effects of forces. For instance, force can change the shape, force can change the size, force can cause an object to change, a moving object change direction. You must have mentioned that force can also cause acceleration or deceleration. That is, a force can cause an object to increase in speed or decrease in speed. So in that unit of force, density, and pressure, you discussed some of the effects of forces. One of the effects of forces that you must have discussed include that force changes shape, or force changes the size of an object. So what does that imply? When an object is subjected to forces, or when forces are applied to an object, or a solid object to be specific, its shape or size is most likely going to change. This change in size and shape of the object is what we call deformation. It's actually the subject of study today. Okay, I want you to follow me very carefully. I'll try to be so slow because it is very important that we try as much as possible to pick the most important points in this very short unit called the deformation of solids. Within the topic, I will mention there are parts where I will mention exercises to be attempted and forwarded for marking. Therefore, it implies that you have to listen and watch the lesson up to the end so that you can be able to attempt the questions which you will submit as your assignment. Okay, so when forces are applied to a solid, its shape or size is most likely going to change, and that change in shape or size of the object is what we call deformation. You must have experienced this in your everyday life. You have blown air into a balloon and you have seen the balloon expanding, and when you try to step on the balloon, you see it getting deformed, and if you apply more force, it ends up bursting. So the change in size, the change in shape of an object when a force is applied is what we call deformation. Actually, deformation is of two types. Deformation can be tensile or it can be compressive. What do we mean by tensile and what do we mean by compressive? Tensile coming from tension, compressive coming from compression. So the deformation basically in one direction is called tensile deformation if and only if an object is stretched out by a pair of forces. So if an object is stretched out by a pair of forces, look at the illustration below. Two forces acting on the same object are tending to stretch it. So we say the object is under tension. In other words, the object is subjected to tensile forces. What will be the effect of applying such forces on such an object? Two things will happen to the object. One, the object can become longer, and two, as the object becomes longer, it becomes thinner. In other words, as the length of the object as L increases, the cross-sectional area decreases. So when an object is subjected to tensile forces, it's most likely going to become longer, in other words, increase in length, and thinner, In other words, decrease in cross-sectional area. So when an object is under tension, it undergoes what we call tensile deformation. If a pair of forces act on an object and squash the object, then we can say that the object is under compressive deformation, or the object undergoes compressive deformation. In fact, these two forces act towards the object in one dimension. Take for instance, look at this illustration here. We have two forces, this force and the other force, acting on the same object. What is the effect of these two forces acting on the same object? The effect will be that the object becomes shorter and thicker. What does that imply? The object decreases in length, L becomes smaller, the length becomes smaller. The object decreases in length, at the same time the object increases in cross-sectional area. That's why we say it becomes thicker. So you must have picked two important things here. One, when an object is subjected to compressive deformation, or when an object is subjected to two forces which tend to compress it, of course the object will become smaller, will become shorter and thicker, as long as it does not buckle. What do I mean? As long as it does not tend to fold in a zigzag fashion, if I'm to put it like that. As long as it does not buckle, the object will decrease in length, in other words become shorter, and increase in cross-sectional area, in other words the thickness becomes bigger. So that's what we mean by tensile deformation and compressive deformation. At your free time, you can try to break a piece of dry stick. You will notice that as you try to bend it, at one point the hands will be moving towards each other, like in this illustration here. So it means the hands will be exerting forces onto the stick towards each other. So one hand is exerting a force in this direction and the other hand is exerting a force in the other direction, meaning that the bottom of the stick is actually under compressive forces. Unfortunately, at the top of the same stick, you will notice that as one hand tries to bend on this side and the other hand tries to bend on the other side, this section of the stick, the upper section of the stick, appears as if there is a force pulling that part in this direction, and there is a force pulling the other part in the other direction. In most cases, you are going to find a crack here very fast because the two forces tend to be pulling apart. So we say that the upper part of that stick will be actually under tension, while the lower part of that will actually be under compression. You must have observed concrete slabs on ceilings, those of you who have ceilings at home made out of concrete. As the ceiling becomes old, or not necessarily the ceiling, it could even be a bridge, it could even be a simple bridge anyway. As the bridge weakens, you will notice when you look at the bridge from any angle, not from top but from any angle or from the bottom, you will notice that the bridge actually easily develops cracks at the bottom. In other words, there could be forces there as you move on the bridge, as people move on the bridge on top, there is a tendency of the bottom of the bridge to be under tension. That's why you notice that there will be cracks developed at the bottom of the bridge, unlike on the top of the bridge where it appears to be under compression, or it appears to be under compressive forces. So in a nutshell, what I was trying to say here is that tensile forces tend to pull apart, and then compressive forces tend to come together, or they tend to squash an object. And then when an object is subjected to tensile forces, or when an object is under tension, it experiences what we call tensile deformation. When an object is under compression, it experiences a form of deformation that we are calling compressive deformation. So let us look at force and deformation. We have seen the difference between compressive deformation and tensile deformation. Let's see the details of force and deformation. Force and deformation. So when actually, if for example you add masses on a spring, if you add a weight on a spring, if you add a mass on a spring, of course it is obvious that the spring is going to stretch, as you can see in that demonstration there. When a mass is added to a spring, it is most likely going to stretch. What would happen if the masses, what would happen if you add more and more weights? You would notice that the string stretches even further, meaning that as you add more and more weights, the stretching increases, and therefore the length of the string is bound to increase. This increase in length of the spring is what we call, or is what we shall be calling, extension in this case. So it will be the extension of the spring, and the weight attached, or the mass attached to the spring, we shall be calling it the load in this case. So as the load is increased, as you add more and more as you add more and more weights to the spring, you will notice, or you will observe, that actually the spring will be stretching further and further and further. So as the load increases, remember I have said the weight or the masses that you'll be adding on the spring is what we shall be calling the load. And then the stretching of the spring, or the change in the length of the spring when the masses are being added, is what we call the extension, or it's what we shall be calling the extension. So you must have observed that as the load is increased gradually, as you add more and more masses, actually the extension increases. So if only the load is increased so greatly, the spring will change its shape permanently. I don't know whether you have seen such springs in the laboratory which have permanently changed their shape. So I don't know if you have seen such springs in the laboratory which have permanently been deformed. So imagine if I added a very, very great load, if I added a very big mass on this spring so that it stretches beyond repair, then the spring will change its shape permanently. However, if I add very small loads, and I remove them like in this demonstration, the spring actually would go back to its original length. So the spring would return to its original length. So because when I put small loads and I remove them, the spring is able to go back to its original length, we say that the spring has undergone what we call an elastic change. We say that the spring has undergone what we call an elastic deformation. So what do I mean by an elastic deformation? For an elastic deformation, if the deforming force is removed from the material is able to go back to its original shape. So when the deforming force is removed, the material is able to go back to its original length. That is, if it has undergone an elastic change. So when somebody talks about a material being deformed elastically, this person is meaning that when the deforming force is removed, the material is able to go back to its original length. The material is able to regain its original length. However, if you put a very great force, If a very great force is used onto the material, even if you remove the force, the material may not go back to its original length. What has happened to the material? We say the material has been deformed plastically. So there's a difference between elastic deformation and plastic deformation. When a material undergoes an elastic change, or when a material extends elastically, or when a material is elastically deformed, if the deforming force is removed or the load is removed, the material is able to regain its original length. The material is able to return to its original shape. The material is able to regain its original length. This is only possible if small loads have been added to the material. Remember, every time you add a load, the extension increases. Every time you add another load, the extension increases. So the extension increases gradually as the load is increased gradually. However, if you put a very great load, a very big load, there is a possibility that when you remove the load, the material does not go back to its original shape. It does not go back to its original length. Therefore, we say the material has been plastically deformed. But if you remove the deforming force from the material and the material goes back to its original length, then you conclude that the material has been elastically deformed, or it has experienced an elastic deformation. If the material does not go back to its original shape, then or its original length, even when the deforming force is removed, then we say that the material has been plastically deformed. So I want you to note the difference between elastic deformation and plastic deformation. A good example of materials which undergo what we call elastic deformation, we have copper, for example, is a very good example of materials which undergo elastic deformation. And that's why you have seen copper being used as many times in the wiring systems of your homes. Copper wires are almost used in our everyday life. We use them for so many electronic applications, simply because of two reasons. Actually, copper can first undergo elastic deformation. At the same time, it can undergo plastic deformation before it breaks. We shall later on see that there are some materials which cannot undergo both elastic deformation and plastic deformation. However, for copper is a very good material that if the loads applied are very small and you remove the loads, the material is able to regain its original length. So we say that the material can easily undergo elastic deformation. However, if you continue increasing the loads onto the material may overstretch, that even if you remove the load, the material does not go back to its original position. So we would say that the material is plastically deformed. So what am I trying to say here? If only you were to plot a graph, assuming you were adding loads onto the material, let me call the load F. This would be in newtons, for example. It is hard for me to write this, but I'm trying. And you are trying to obtain the extension. Remember, extension in this case being the new length minus the original length. Let me say you obtain the extension in centimeters of the material. So when the loads added to the material are very small, you would notice that there is an extension, and when you remove the load, the material goes back to its original shape or its original length. That's why as you add the load, for example, let me say you start with 1 Newton, you may notice that the extension is, say, 0.1 centimeters. When you add 2 newtons, you may find that the extension is, say, let me say proportionality is 0.2 centimeters. Of course, it can't be perfectly proportional, but you would draw a line of best fit. Maybe when you add 3 newtons, a load of 3 newtons, you would notice that the extension is, say, 0.3 centimeters. And if you plot a graph of force against extension, you would notice that it is a straight line. So this straight line indicates that for small loads, for very small loads, extension is directly proportional to the force. In other words, for very small loads, extension is directly proportional to the force, or force is directly proportional to the extension. For small loads or for very small weights, extension is directly proportional to the force, or for small forces, extension is directly proportional to the force. But as you continue adding loads, as you continue adding, remember you are adding and removing, and you see the material going back to its original shape. You add the load and you remove, you see the material going back to its original shape. Then there is a point where you add the load, and when you remove, the material does not actually go back to its original shape. Initially, when the extension is directly proportional to its original length, you will get a perfectly straight line. The point P is called the proportionality limit. At this point, the force, this is the maximum force for which the extension will be directly proportional to the force. So when you continue adding loads onto the wire, onto the material, maybe it was a spring, I always prefer to use a spring. So you were adding masses, you were adding loads to the spring. So if you continue adding loads, there is a point where, first of all, you have added a very big, maybe you are adding for the 50th Newton, you are adding to get 5 Newtons. You notice that actually the extension is not, the pattern of the extension is not as it was before. Maybe let's say for 4, it was actually 0.4 centimeters. But you notice that when you add 5, and 5 is a very big load, you will notice that the extension actually is not, the difference between the extension is not the same as before. Maybe it could be, you will notice that the extension is actually 0.3. Maybe 0.3. So it means now, or it can be 0.41. Let me say 0.41 because it could be increasing still. Let me say 0.42. So it means you have added the load, which is very big, and the extension is no longer proportional to the applied force. So there is that region where when you remove the material, it goes back to its original shape or its original length, but the extension is not directly proportional to the applied force or to the load. So until a certain weight, until a certain force, or until a certain load, where now beyond that load, the material cannot even go back to its original shape. So beyond this point here, which we call the elastic limit, this elastic limit refers to actually the maximum force that can be applied to a material such that it returns to its original length when the force is removed. That's what we call elastic limit. When someone talks about the elastic limit, is actually referring to the maximum force that can be applied to a wire or to a material such that it returns to its original length when this force is removed. That's what we mean by elastic limit. So if you continue adding loads, then you'll go beyond the elastic limit. Beyond the elastic limit, of course, force will not be directly proportional to extension. You may find that for a material, you add a very small force and you get a very big extension, or to get a small extension, you may put a very large force. So the reverse is also true. To get a small extension, you may need a very large force, or a very small force gives a very big extension. Like for this, for example, this diagram here is indicating that for beyond a point E, you would notice that a very small change in force will give a very large extension. That is what it means, because you see it is flattening and so on and so forth. So a very small force is giving a very large extension. So here force is not directly proportional to the extension, and If a very small force gives a very large extension, it implies that even if you remove the deforming force, the material does not go back to its original shape or its original length. Therefore, we say that the material has been plastically deformed. Between O and E, the material is elastically deformed, because when the deforming force is removed, the material can go back to its original shape or its original length. Between O and P, the force is directly proportional to the extension. When you increase the force by equal amounts, the extension of the material increases by equal amounts. That's why you have a very straight line. Beyond the P, yes, you can add a force and there is an extension, and when you remove the force, the material goes back to its original shape, but the extension is not directly proportional to the applied force. So this graph here can also be drawn in such a way that after beyond this graph can even go up. It can go up to mean that you will require to mean that a very large force may give a very small extension. So it means I can also draw this graph going upwards. That beyond E, you may notice that to give a very small extension, maybe I'm drawing it in a note, I'm not drawing it the way I want it. I can draw it like this. So here beyond E, it implies that a very large force is giving a very small extension. I don't know whether you can see the change in extension is very small. Yet for the one in the blue, a very small force is giving a large extension. Remember, on the x-axis we have the extension. So I want you to note very carefully the section of the line from P to the origin. From P to the origin is a straight line. In this region, I have just mentioned that the force or the load applied on the spring or the load applied on the material is directly proportional to the extension, or the extension is directly proportional to the load. And I mentioned that point P is actually called the proportionality limit. Point E, I called it the elastic limit, or the limit of elastic behavior. And it should always come beyond the P, the limit of elastic behavior. So the spring which I'm using here is actually deformed permanently beyond point E. The spring is going to be deformed permanently, that even if you remove the deforming force, it will not go back to its original length. So we say it is deformed permanently, therefore it has experienced what we call a plastic change. It has undergone what we call plastic deformation. So what happens beyond E actually? What happens beyond E? I don't know whether you have ever stretched a plastic material. For example, a piece of polythene. You try to stretch it. You will notice that somewhere, of course when you are stretching it, you are applying tension forces on it. The material will be under tension. So you will see that between the material, when you try to stretch it, you see as if the particles, the molecules have moved apart. It appears as if the molecules have slided past each other. So what happens beyond E? When you continue adding forces onto the material and you exceed the elastic limit, the molecules in the material slide past each other. That's why we say the material is deformed permanently. So it will be an irreversible deformation. It is said to undergo what we call plastic deformation, or to have what we call a plastic behavior. I want you at your free time get a polythene and try to stretch it with your two hands, and then look at the polythene. You will notice as if the molecules have slided past each other, and there is a point which is going to be more faint compared to others, meaning that at that point the molecules have slid past each other. That is what we call plastic deformation. So a material like a copper, which can first of all undergo elastic deformation and later undergo plastic deformation before we reach point B, B is the point where the material now breaks. You can call it the breaking point. A material which undergoes both elastic deformation and plastic deformation before it breaks is what we call a ductile material. A ductile material. That material which undergoes both elastic deformation and plastic deformation before it breaks, it is called ductile material. So the behavior of undergoing both elastic deformation and plastic deformation before breaking can easily be called ductility. So you should know what we mean by ductile material. Good examples of such materials which can undergo both elastic deformation and plastic deformation before they break, we have copper. That's why you see copper can be rolled into several shapes. We have gold. Gold is another example of metals which can be, is a good example of a metal which can be rolled into several shapes. It can be stretched, it can be hammered, it can be squashed. That's why you see you can buy very beautiful jewelry made out of gold, because gold is ductile. You can, they sometimes they make jewelry out of copper and then the gold coat it, and they sell to you expensively and you think it is even gold, yet it is just copper which is gold coated. So such materials can easily be molded into any shape because they undergo both plastic deformation and elastic deformation before they break. Okay, so taking you back to the graph, the fact that there is a straight line relationship between the load applied, which is the force, and the extension of a material is expressed in a law which we call Hooke's law. A law which we call Hooke's law. So the straight line relationship between the load and the extension is actually explained in details in a law which we call Hooke's law, in the memory of Robert Hooke, the first scientist to try and investigate the behavior of materials when they are being loaded. So in this the straight line relationship indicates that force is directly proportional to the extension. Actually that is Hooke's law, but we have seen this was only possible for the first small loads, 1, 2, 3, when the load is very small, or for small loads force is directly proportional to extension, or for small, of course small loads will result into small extensions. So in other words, I can also say that for small extensions force is directly proportional to extension. That is what we call Hooke's law. This is only possible in most cases if the elastic limit is not exceeded. So we can state Hooke's law that for small extensions the force is directly proportional to the extension. Or we can say that for small loads, the force is directly proportional to the extension. For very large loads, we have seen that for very large loads, the force may not be directly proportional to the extension. So if I try to remove the proportionality sign from this equation, or from this expression here, F directly proportional to E, then it means F will therefore be equal to a constant, call it K, times the extension E. I've removed the proportionality sign, I've brought in the constant and the equal signs. So this is actually called Hooke's law. Precisely that is Hooke's law. So when somebody talks about Hooke's law, is talking about F directly proportional to E. In most cases, instead of using E for extension, you will find there X used for extension. So the force can be the tension or the force acting on the material. Then E is actually the extension, where you and me know that to find the extension we need to see the new length. We note the new length of the material, call it L. We subtract the original length, which is L0. That means before loading the material you need to measure or to record the original length, so that when you load the material, now you can get the new length minus the original length L0. That will give you the extension. Then what is K? K, the constant K. From this graph here, because it is force against extension, it means the gradient of this graph will be the constant k. That is, from the graph you can see that the constant k therefore is equal to change in f. I will use change in f for us who know mathematics. A change in f divided by a change, let me say change in extension delta E. So the constant k is called the material constant. If it is a spring, I will call it the spring constant. If it is a wire, then I will call it the wire constant. So I always prefer to call it force constant, because the material may not be a spring, the material may not be a wire, so it is just a force constant. So what could the units of this force constant therefore be? So because it is in 4, it is we are obtaining it from here. We have plotted f. You have plotted the graph of f against E. That means the gradient is the constant k. So f over E, that means the units of the constant k will be, the derived units will be therefore Newton, because force is in newtons, and then the extension is a distance whose SI unit is, or it is a length whose SI unit is meters. So this will be newtons per meter. You can go ahead and obtain the base units of the force constant k. So that is Hooke's law. For small extensions, force is directly proportional to the extension, or for small loads, the force is going to be directly proportional to the extension. Some people prefer to state that provided the elastic limit is not exceeded, the extension of a material is proportional to the applied force. However, there is a point, the proportionality limit, the elastic limit is always beyond the proportionality limit. And yet, beyond the proportionality limit, the extension is not directly proportional to the applied force. Yet, between the proportionality limit and the elastic limit, the material could still go back to its original shape. So that means it's better to state Hooke's law as, because the Hooke's law corresponds to the straight line, to the straight part of the graph, then it's better to state Hooke's law that for small extensions, the force is actually directly proportional to the extension. Or for small loads, the force is directly proportional to the extension. That is what we call Hooke's law. I have removed the proportionality sign and included and brought in the equal signs and the constant. And the constant from the straight line part of the graph, we called it the spring constant, or the material constant, or the force constant of the material, whose SI units would be therefore newtons per meter. So I want you to note something from Hooke's law. Remember, Hooke's law will correspond to the straight line part of the graph, where the force is actually directly proportional to the extension. What does that imply? If there is no applied force, the extension of the material must be 0. So how do you verify? Suppose you have, many times we shall face graphs which do not start from the origin 0, 0. Maybe they could be starting from somewhere hanging in space, or maybe having false origins. By the way, a graph with a false origin is a graph whose axes are not starting from 0, 0. Maybe as you have studied, you have been seeing graphs where you may find on one axis it starts from 2, the other axis starts from 6. These are called false origins. So if you have such a graph, maybe you have such a graph, and you could be having a straight line. You could be having a straight line, and you may want to verify whether the graph indicates that the material obeys Hooke's law. Or how would you verify from the graph that the material obeys Hooke's law? Remember, force should be directly proportional to the extension. That if the force is 0, the extension should be 0. That means the graph should not have an intercept. The graph should not have an intercept. And how do you verify that? From f equals to k, from f equals to maybe k, that is a constant times the extension. The force is equal to the constant times the extension, and you have plotted a graph of force against the extension. The gradient would be the constant. But how do you verify the material is obeying Hooke's law. So you will have to look at the equation of a straight line, y equals to mx plus c. If a graph starts from the origin 0, 0, even if they have not drawn it to start from the origin, then the intercept c should be equal to 0. The intercept should be equal to 0. So if you have a graph of force against extension, or it can be extension against force. Maybe I forgot to mention that normally a graph of extension against force is plotted rather than force against extension. When we study planning and analysis, we shall note that normally on the x-axis we prefer to put there what we call the independent variable, and on the y-axis we prefer to put there the dependent variable. So what determines the other? What depends on the other? Is it the extension or it is the force? Actually, the extension depends on the force. You will not have an extension when there is no force. So when you change the force, that's when you will have a change in the extension. So we shall call the force is independent because it is changed by the experimenter. The extension is dependent because it changes when the experimenter changes the force. So normally you will find that this graph, instead of plotting a graph or drawing a graph of force against extension, you may find out that instead it is a graph of extension against the force which is being plotted, because normally, like I've mentioned, that in a planning and analysis we shall be mentioning and talking about dependent and independent variables. Normally an independent variable is changed by the experimenter. When you want extensions of a material, you are the one adding masses, or you are the one adding loads on the spring. So the loads you are adding, those are the forces. So when you add a load, that is a force. The presence of a force will change the extension. So the extension is depending on the change in the force. So the force is the independent variable and the extension is the independent variable. So you may see sometimes graphs drawn like this. In this case, it doesn't require you to be a genius to know that the gradient of a graph of extension against f is actually 1 over k, because if you already know that force is equal to ke, if force is equal to ke, and then you make E the subject, because E is on the y-axis, you notice that E will be equal to F 1 over K times 1 over K times F. 1 over K times F. What does that imply? If a graph of extension against F is plotted, it means the gradient is 1 over K, where K is the material, the force constant, or the material constant. So I was saying that if you want to verify that a material obeys Hooke's law, provided the elastic limit is not exceeded, the extension of a material is normally proportional to the applied force, especially for small extensions. For small extensions, force is directly proportional to the extension of the material. That is the right way of stating Hooke's law. So if you want to verify that the graph shows, or the graph is for a material which obeys Hooke's law, it is very simple. Obtain the gradient. Use coordinates from the line. Maybe you can choose a point on the line. You read the y coordinate and x coordinate. Substitute into the equation of a straight line. Once you obtain that c equals to 0, it means the graph, even if it is having a false origin, it means somewhere it would have started from 0, 0. So first of all, it is a straight line. Number 2, with starting from the origin. So if c equals to 0, the line passes through the origin. That means it has no y-intercept. If it has no y-intercept, it means force is proportional to extension. If a graph has a y-intercept, if c is not equal to 0, if C is not equal to 0, and that means it will be having a y-intercept. If the graph has y-intercept, it means that the force in this case is not 0 when the extension is 0, or the extension is not 0 when the force is 0. It means that the material does not obey Hooke's law. The material does not obey Hooke's law. So I want you to note very carefully that a stiff material, or a stiff material, or a stiff spring, for example, or material, will have a very large value for the force constant. Maybe I can demonstrate this. Okay, so the extent to which a material deforms is going to depend on what we call its stiffness. How stiff is a material? You could be having two materials, for example, springs of the same length exactly, but they don't stretch to the same length even if you apply the same force, or even if you add the same load. That is now what we call stiffness. They could be made of the same material but having different dimensions. What do I mean in this case? They could be having different thickness, making one material stiffer than another. Let's see this illustration here. Here I had two springs. For one spring, you can see I added 200 grams. And I even added more 200, so that I had 400 grams. Look at the extent to which the spring would extend. It means to get a small extension, I needed a lot of force, and I needed to add more load. Now look at the second spring. For the same load, for the second spring of equal length to the other one, the same load would give a very big extension. What does that imply? One spring is stiffer than another, even if they could be of the same length. This spring is stiffer than the other, even if they could be of the same length. What could be the reason? One could be having a different thickness as compared to another spring. That is what we call stiffness. So when we talk about stiffness, two materials may not stretch, may not experience the same extension, even if the same force or the same load is added, because they have different stiffness. So a material which is very stiff has a bigger force constant. I think it makes sense, because the force is directly proportional to the extension. It means the material which is very stiff, it has a bigger extension, a bigger force constant K. So K, because K is equal to F over E, that is if you consider force being directly proportional to extension. So a material which is very stiff requires a very big value of F to cause a very small value of E. That means it has a very big value of the force constant. It will stretch by a small extension for a very big F. A material which is less stiff has a very small value of K, because a very small force F would cause a very big extension. Look at this illustration that we have just seen here. These two springs, spring A and B. Spring A requires, or spring A would extend it would extend so far for the same 400 grams. But look at spring B. Spring B is almost, actually it has not even stretched to half of the other spring's length, yet the load is the same. So it means spring B is more stiffer than spring A, and it implies that spring B has a bigger force constant. It requires a very big force to cause a very small extension. It requires a very big force to cause a very small extension, implying that the constant K is very big. So when the material is very stiff, it means it requires more force to give a very small extension. So if you were to plot two graphs, if I was to plot a graph of a spring A which is less stiff than spring B, then it means the force against extension graph for this spring here, which is very stiff, which is more stiff, will be more steeper than the force against extension graph for the other spring, because for this spring here a very big force gives a very small extension. Maybe let me put that on paper. So what I'm trying to say is that if I was to sketch a graph of force against extension for the two, so I'm sketching the graph on the same axis for the two springs, that is for force against extension, and this is what I will observe. Because spring A was less stiffer than spring B, the spring B is the one which had a very small extension for 400 grams, and spring A is the one which could extend like nothing for the same 400 grams. So it means if I was to sketch a graph of force against extension, if Hooke's law is obeyed, these graphs should start from 0, 0. So these two graphs will start from the origin. But for the one which is stiffer, it requires a very large force to give a very small extension. So the graph will actually be steeper. So this is for spring B, which could not easily extend even if we added 400 grams. But for the one which is less stiffer, a very small force causes a very large extension. So for that one, the graph will be below. So this is more stiffer than this one here. You could even find a gradient. The gradient of this graph indicates that the value of K here is far bigger than the value of K here. If you try to find a gradient of this line, it means that the value of K here is actually smaller than the value of K in the other case. So that is what we call stiffness. So the extent to which a material stretches will also depend on how stiff the material is. Some materials are extremely stiff, some materials are less stiff. Two materials, for example, two springs can be made from the same material but of different masses and density, even if they have the same length. Such springs, you don't expect them to extend or to stretch by the same extent. So one will be stiffer than another because of the thickness or the diameter of the wire used to coil to make one spring will make it more stiffer or less stiffer than the other spring. So you should be able to identify which materials are stiffer by looking at the graphs, and you should be able to explain why you may think that such materials are actually stiffer. I've told you that if a material is stiffer, it means it requires a very large force actually to give a very small extension, which implies that the material constant or the force constant of such a stiff material is actually going to be very, very high. Okay, so let's try to investigate springs. We are going to try and investigate springs. Remember, we have talked about stiffness of a material. So if a material is very stiff, then it means it will require a very large force for it to stretch actually. So I want you to remember that if a material is extended elastically or is deformed elastically, I have just mentioned and said for such a material, if the deforming force is removed, the material actually regains its original length or maybe shape. If the material does not actually regain its original length or its original shape, then we can conclude that the material has actually been permanently deformed. Therefore, it means the material has undergone what we call a plastic deformation. I want us to try and investigate springs. What happens if springs are connected in series, and what happens if springs are connected in parallel? Maybe before we advance, I want you to observe what I was doing in the lab. So this is what I was actually doing. I tried to first of all look at an individual spring. I'll try to skip some of these. So I loaded it with a mass and I noted its extension. Of course, after knowing the original length, I loaded it with a mass and I noted the extension between the change in length when it is loaded with a mass. So I got two other identical springs, and now I checked and noticed that the length is the same. You can see me checking to find out that the lengths are the same. I try to ensure that the springs are identical, and so I was trying to fit them such that they are joined end to end, so that we can have what we call a series combination. I think I was trying to recheck and see actually the initial length of the second spring, so that I cannot make a very big error when I join them end to end. So of course, not ignoring the parallax error, because the ruler was far away from the spring. The ruler was not very close to the spring, and you notice that I didn't have a pointer on the spring. So ignoring the parallax error of reading a scale, I was able to tell the length of the spring. And then now I decided to join the springs together so that they would be in series. So what happens to the extension when they are in series? Now, one thing you have to note here is that this spring at the top is actually supporting the one at the bottom. So you notice that there will be another error due to the weight of the second spring. So this because the extension of this spring on top will actually be as a result of the weight of the second spring, and also as a result of the mass which is being added. But assuming that the springs are very light, that their mass is very small, therefore the effect due to the weight of the second spring onto the first spring is very, very, very small, and I can neglect it for now. So I load the springs now. What do I observe? I noticed that the spring at the top extends as well as the spring at the bottom. And when I checked the extensions, I noticed that the total extension is actually the extension of the first spring plus the extension of the second spring. But I want you to note very carefully that the two springs are supporting the same load. What does that imply? Whether they are not identical at all, especially when it comes to the force constant, even if the spring constant K of the first spring is not the same as that of the second spring, but they are supporting the same load, meaning that they are experiencing the same tension. So the tension in the second spring is the same tension in the first spring because they are supporting the same load. However, the extension may not be the same. but the extension is the sum of the extension in these springs when they are connected in series. So the total extension when a load is added will be the extension of this spring. If I knew its original length, now I can measure its new length when the load is added, plus the extension of the other spring. If I knew its original length, then I can know its new length when a load is added. So that is actually what I was doing. So you notice the two springs are supporting the same load, implying that the tension they experience is the same because they are joined end to end. But the extension may not be the same if the springs are not identical. Now let's see what happens when we connect them when we connect them in such a way that they are parallel. So I tried to put them on the load, and I used a wooden rod to act as my support for the mass. You can see what I was doing. Of course, the springs were not perfectly equal in length. I just made an approximation, especially the loops. One of the springs had a loose loop, but I know it indicated exactly what I wanted. So looking at the springs, I could first of all note the initial length before putting the mass, and when I added the mass, you could see how small the extension was. What does that imply? When springs are connected in series, we have seen that the total extension is actually the sum of the extensions of these springs. They support the same load. They feel the same tension. They experience the same tension. But what happens when the springs are connected in parallel? We see that the extension is even smaller than the extension of one spring. What does that imply? When springs are connected in series, the extension adds up. It is bigger than the extension of one spring. When springs are connected in parallel, connecting springs in parallel reduces the effective extension, because we see that when they are connected in parallel, actually the extension of the springs is even smaller than it would be if you had only one spring. That was actually my observation. What does that imply? Why is it that the springs now extend to a smaller distance when they are connected in parallel? The reason is very simple. When they are connected in parallel, it is like they share the load. They share the load depending on how stiff each spring is. Actually, the more stiffer spring dictates the extension. The more stiff spring will dictate the extension. They share the load, and the more stiff spring will actually dictate the extension. So if these two springs were actually identical to each other, then the extension when they are connected in parallel will be a half of the extension which an individual spring would have if the same load is attached onto the spring. Meaning that if they are identical and connected in parallel, they actually share the load equally. What does that mean? They would share the load equally if they were identical. That means the tension experienced in this will be the same tension experienced in this, but the sum of the tension experienced in both springs will be equal to the load. If they are not the same, if they are not identical, then this spring will experience its own tension depending on its stiffness. The other spring will also experience its own tension depending on its stiffness, but the sum of the tensions experienced should be equal to the load they are supporting. So when springs are connected in parallel, actually the total or the effective extension will reduce. The total tension of the two springs is equal to the weight or the force, the load they are actually supporting. Okay, I went ahead and gave you a bonus. The bonus that I gave was to add another spring almost identical to the two springs, and I want you to note that for it even stretches further because it appears to be in series with the parallel combination. So you notice that the two springs are in parallel and their combination is actually in series with the spring at the bottom. And you notice that the spring at the bottom, for it stretches further, it stretches more, but the springs at the top are not stretching more. In fact, here, if the springs were identical, perfectly identical, the extension of the two will be a half of the extension of one spring plus the extension of this spring here. This spring will also extend, and actually this one will extend if the extension of one spring is x with this load. That means when the two are in parallel, the extension of them, their total effective extension will be a half x, and then the extension, this one will extend fully because it is supporting this load here. Although these two are sharing the load, this one is actually experiencing the whole of this load. So the total force here will be the force in this spring plus the force in the other spring. But again, the sum of the force here will be actually the force experienced by this spring here. So the total tension experienced by the two springs is the same as the tension experienced by only one spring, because this one spring is in series with the parallel combination. Remember, we said when springs are in series, they experience the same tension. Now, when they are in parallel, the tension, the load is shared depending on their spring constant. So they share the load such that the total tension of the two springs is equal to the load. Now that this one is in series, it is actually experiencing a tension because it is lifting, or it is holding this load. And the tension it experiences is the same as the effective tension experienced by the two springs if connected in parallel. Okay, I think that was all that I did in the laboratory. Ignore the errors that were involved. I gave even a bonus of two springs. I gave you a bonus of two springs here. I first recorded. That was very, very long. I had to change the mass because the other mass couldn't give me what I wanted. You could notice that when I tried with one initial spring, I could tell how long it extended easily, and when I connected them in parallel, let me see, when they are in parallel, I try to add the load. Of course, I'm trying to ignore the weight of this rod here because it is very light. It is a dry piece of wood, therefore its weight is very small. But when I added the mass, to my surprise, the extension was even very small. In fact, it's like the springs did not extend. And I told you when springs are connected in parallel, they actually share the load. They share the weight. So it means the tension in each spring, if they are perfectly identical, the tension in each spring is the same, but the sum of the tension is in the springs is actually equal to the load for equilibrium. And if they were connected in series, then the tension is added up because they are supporting the same load. The tension is the same actually. So the tension experienced by one spring is going to be the same as the tension experienced by another one. So it means the tension is the same. They would be supporting the same load if they were in series. If they are in parallel, the tension experienced in this one and the other one will be equal to the load. So the tension will be smaller in each spring, but the sum of the tensions will be equal to the load they are supporting because they actually share the load. So thank you for watching that demonstration. I can take you back to your class. So we have seen that when springs are actually joined in series, they support the same load, F. So they experience the same tension. So what am I saying? For the first diagram where they are in series, you will notice therefore that the force F1, which is the tension in the first spring, is actually the same as the force F2, which is the tension in the same spring, which will be actually the force F, which is the load. In other words, even if you had one spring, it would support the load. That would be equal to F. Even if you had the second one, it would support the same load and would extend the same amount. That would be equal to F. So that means when you use them in series, join them end to end, they support the same load. They experience the same tension. They experience the same tension. So F, the force will be the same. The force in each spring, which I'm calling the tension, will be the same, but the extension may not be the same depending on how stiff one material is. So because the extension may not be the same, then the total extension, which I'm calling X, would be equal to, say, X1, if X1 is the extension in the first spring, added to X2 if X2 is the extension in the second spring. Okay, so if that is very true, and F1 equals to F2, which is equal to F. So what is F1? From this first spring here, you and me would notice that F1 from the first spring is going to be equal to K1 times X1. F1 is going to be K1 times X1. We are using we are using Hooke's law. Hooke's law, force directly proportional to extension. Then that is F1. Then F2, from the second spring, you'll notice that F2 is going to be equal to K2 times X2. My handwriting may not be good, but I know you understand. But remember, we have said F1 is equal to F2 is equal to F. So it means if I make X1 the subject in this equation here, make X1 the subject, make X2 the subject here, and then from Hooke's law, therefore F is supposed to be equal to Kx, where now K is going to be equal to the effective spring constant, I'm calling it K, and X is going to be equal to the effective extension or the total extension X. So I'm substituting, I'm making the X as the subject and substituting this equation here. So if I make the X as the subject and I substitute in this equation here, putting in mind that F1 equals to F2 equals to F. So if I make the X as the subject and substitute into these equations here, then this will be actually F over K. This will be F over K. F over K. The second X1 will be actually F over K1. Remember, I said F1 is the same as F2, which is the same as F, because they support the same load, they experience the same tension. So it means the tension in each spring is the same as the load they support. So this will be plus F divided by, actually this was X2. So this will be F divided by K2. So if that is F divided by K2, and then F has cancelled, you will notice that the effective spring constant is actually obtained from the sum of the reciprocals. So 1 over K is going to be equal to 1 over K1 plus 1 over K2. What does this imply? It means that when springs are in series, they are behaving like resistors in parallel. We shall see that in electricity. Remember, in parallel, those of you who have seen it in IGCSE or in your O level, you have seen that for resistors in parallel, the effective resistance is obtained from the reciprocals. So if I have only two resistors, if I have only two springs, then the effective spring constant K is going to be equal to, I'm making the LCM and so on and so forth. This will be the product. That will be K1, K2, K1, K2 divided by the sum, which is K1 plus K2. K1 plus in French they say plus K2. So that is the effective spring constant. Now if I say that the springs are identical, meaning that they have the same dimensions, so they have the same spring constant, let me call it K. If the springs are identical, I'm just making an assumption that every spring has spring constant K. In other words, K1 is going to be equal to K2. If K1 equals to K2, which is equal to K, then what will be the total effective spring constant? Let me call it K total KT. So if the springs are identical, each with the spring constant K, because in the exams they will give you springs which are identical, each with the spring constant K. So in this case, if the springs are identical, each with the spring constant K, it means K1 and K2 are the same. So I'm substituting in this formula, this expression here. So K total will be K times K over K plus K, which is going to be equal to K squared. That will be K squared divided by 2K. So it means the effective spring constant, if springs are in series, will be half of the spring constant of just one spring. If you have two springs in series, the effective spring constant is actually half. The effective spring constant is actually half the spring constant of just one spring. What does that mean? Connecting springs in series reduces the spring constant. Connecting springs in series reduces the effective spring constant, because we are seeing it is half the spring constant of just one spring. So when you have springs, only two springs in series, the effective spring constant is the product of the constants over the sum, because they are treated the same way you would treat resistors in parallel. By the way, if you have so many springs in series, remember we get the effective spring constant from the reciprocals. That implies if I had so many springs in series, so I would add here plus maybe 1 over K3 plus and so on and so forth. That is if I have so many springs connected in series. But one thing you need to note is that when springs are connected in series, the effective spring constant is smaller than the spring constant of just one spring. However, the extension is higher than the extension of just one spring, because the extensions add up. I think I've made myself clear on that. Now suppose the springs are now in parallel. For example, in example B, if the springs are in parallel, remember I said they share the load, so that is why you see the extension is very small, because they share the load, so that the tension experienced by one spring plus the tension experienced by the other spring is equal to the load. So that means in this case F is the same as F1 plus F2. So F will be the same as F1 plus, or plus in French, you know I'm learning French, I like it so much, F1 plus F2. That will be the effective tension in the springs. So if F equals to F1 plus F2, what is F1? F1 will be equal to, by the way, if the springs are connected in parallel, actually they extend by the same amount. Even if they are not identical, they stretch by the same amount. Remember, the others in series, they experience the same tension. Those ones in parallel, they stretch by the same amount. Actually, the extension to which they stretch is normally dictated by the more stiffer spring. The spring which is stiffer will dictate how far the system stretches. So they stretch by the same amount. Let's call this x. So that means the extension of this spring will be the same extension of the other one if the system is horizontal. If initially you measure the length of the system, then you add the load, you measure the new length, you'll notice that the extension for the two springs is going to be the same. What does that imply? F1 for this F1 for the other spring is going to be equal to K1 times X1. Even if they are not the same, they have different spring constants, they will extend by the same amount. So F1 will be equal to K1 times X, and then F2 will also be equal to K2 times X. So F2 is going to be equal to K2 times X. K2 times X. But remember, F is F1 plus F2. But what is F? In terms of X, if X is the effective extension, then F is going to be equal to K times X, where K is the effective spring constant of these two springs connected in parallel, and X is the effective extension. So if the springs are connected in parallel, the extension is the same, X. So X is even the effective spring constant. So since F is equal to F1 plus F2, I'm substituting into this equation here. So F is Kx, F is Kx, F is Kx equals to F1, which is K1 X1, K1 X, because the extension is the same, so that will be K1 X, plus F2, which is K2 X, because the extension is the same for springs in parallel, so that will be K2 X. You and me notice that the X cancels out, so X has cancelled out in this equation, and therefore K is going to be equal to K1 plus or plus K2. What does that imply? When springs are connected in parallel, the effective the effective spring constant is the sum of the spring constants. In other words, connecting springs in parallel increases the spring constant. Connecting springs in parallel increases the spring constant. Connecting springs in series reduces the spring constant. So it means if you have only two springs, if you have any springs connected in parallel, if the springs are identical, the total spring constant, let me call it Kt, if the springs are identical, each with the spring constant K, then total spring constant, if there are n springs, then it should be n times K. N times K. Here there were 2, so it will be 2K. Total spring constant will be 2K if the springs are connected in parallel. So if there were so many, and let me say there are n springs, each having spring constant K, the effective spring constant is actually n times K. So when the springs are connected in parallel, the effective spring constant is the sum. When springs are connected in series, the effective spring constant is obtained from reciprocals. Remember, connecting springs in series reduces the spring constant. Connecting springs in parallel increases the spring constant. And remember, the bigger the spring constant, the smaller the extension. So it means connecting springs in parallel increases the stiffness of the system, implying that when springs are in parallel, it requires a bigger force to give a smaller extension. If systems are in series, it requires a smaller force to give a bigger extension. If systems are in parallel, having more springs in parallel increases the spring constant or the effective constant. And if the spring constant is higher, it means the system is more stiffer. If the system is more stiffer, it means it requires a large force to give a very small extension. So having more springs in parallel means higher stiffness of the system. Having more springs in series, it means smaller stiffness of the system. I think I have made that very, very clear. Let's see one example and we hang up from there. In this example, some identical springs, each with a spring constant K, are arranged as shown in the figure. So they are saying they are identical, each with a spring constant K. So this has spring constant K, spring constant K, spring constant K. Okay. Arrangement is here. They want to find the total extension and the spring constant of the arrangement. The load on each of the arrangement is L. Complete the table by determining the total extension in terms of E. So we want total extension in terms of E and the spring constant in terms of K. So if you have one spring connected supporting the load L, it will extend by extension E. Now if they are in parallel, then the extension reduces. It will actually be a half E. So the extension will be a half E when they are in parallel. So the extension here is a half E, because connecting the springs in parallel reduces the extension. So the extension here is a half E. Why am I writing very poorly? What is wrong with me? Ngamije would say that the ancestors are holding my hand, but I am trying my level best to write very well. So here the extension should be a half E. So the system in parallel, the extension, total extension here is a half E. The extension reduces, it becomes smaller than the extension of just one individual spring. Because this one is only alone, its extension will be E. So what's therefore the total extension? So the total extension there will be a half E plus E. That will be a half E. Let me see, a half E plus E. And this gives you, I think this is LCM is 2, that is 3E. That will be 3 over 2. I think that is 3 over 2E. So the total extension here will be 3 over 2E. 3 over 2E. What will be the spring constant? I will notice that the spring constant will be 2 over 3K. I'll tell you how, the simple rule. So let's find the spring constant. These ones are in parallel. How do you get spring constant in parallel? The spring constant in parallel is actually the sum. So the spring constant in parallel here will be actually K plus K. For the parallel combination, the spring constant is 2K. Let me use a different color for the constants on the diagram. For the parallel combination, the spring constant is 2K. Because they are in parallel, we sum up the spring constants. But the 2K is going to be in series with the K. So here this one is K. So the 2K is going to be in series with the K. Then what will be the effective? Remember, when springs are in series, we use the reciprocals. So this will be 1 over the effective, which I'm going to call KT to mean total spring constant, should be equal to 1 over 2K. 1 over 2K plus 1 over K, because they are in a series. So this is going to be a product over sum to get the total spring constant, which I'm calling KT. So K total will be product. The product is 2K times K, which is 2K squared. 2K squared divided by the sum. The sum is 2K plus K, which is 3K. 3K. This is going to give me, you see that 1K cancels and have 2 over 3 times K. So I think I mentioned, before I did this, I mentioned that this is 2 over 3K. It is not magic. I just looked at the total extension. if the total extension is 3/2e, then the what? The spring constant is the reciprocal of this value here. You see this? Because when the extension is bigger, the k is smaller. They are inversely proportional. So it means if I have finished to find the extension, and I see that the extension is 3/2e, then the effective spring constant is the reciprocal. You just reverse this. You can try it out. It will work for all systems. As an assignment now, have 4 resistor. We are going to have one, that is one spring, two springs. Those ones are in series, and then they are connected in parallel with another system. This is one spring, 2 springs, so that we now have another system of, we have that system. These are 1 spring, 2, 3, 4. This is spring 1. I want you to note very carefully. This is 1 spring, second one, another spring, and the system is again connected in series with another spring which is at the bottom, and is the one supporting the load. So it is the one supporting the load L. Now I want you to find the total extension and also find the spring constant. I want you to verify. First, find total extension and see that, and write the answer to be the reciprocal. You find the reciprocal of this fraction here. You just add there a k. That will be the spring constant. Then go ahead and work out the spring constant. I mean the effective spring constant. Note that each resistor, not resistor, I don't know why I fancy resistors so much. Each spring is having spring constant k. Let each spring have spring constant k. Find total extension in terms of E, and find the effective spring constant in terms of k. I think I should stop here for now. So thank you for watching my lesson. I hope you have picked a few important things. When we meet in class, we shall just discuss a few questions regarding the same thing. If you have a question, write it somewhere, so that when I come to class and I say that it is time for discussion, we are going to it's time to discuss deformation, you raise your question. However, I will not teach this in class as a topic. We shall just have one lesson and we summarize it. Thank you for watching my lesson. Remember to subscribe, share, comment, leave a comment, leave a complaint, no problem. I'll always attend to it. Thank you. Stay home and stay nice, stay safe. I love you all. Bye.